Today, we are going to talk about really two topics that honestly don't have a whole heck of a lot to do with each other, but they're relatively short, so I'm lumping them together. So the first topic that I want to talk about is what's called source combination. And this is incredibly similar to resistor combination that we covered in our last class meeting, right? So we talked about the concept of electrical equivalence and said that if we had, let's say, a voltage source, 10 volts, connected to some network of a 10 ohm resistor, this was electrically equivalent to that same 10 volt source connected to two 20 ohm resistors in parallel. And then from there, we actually went into the rules of combining those equivalent resistances, right? So we were looking at electrical equivalence from the perspective of the source, where our constraint was that the voltage drop over our resistor network, V, and the current flowing into our resistor network, I, were identical in both cases. We can do the same thing from the perspective of a resistor in order to figure out how to combine voltage and current sources, okay? So let's start by talking about voltage sources in series. So let's say that I have the following network of voltage sources, where I have some voltage V1, and then I have some voltage V2 connected to some arbitrary resistance R. The voltage drop across my terminals here will be V, and the current flowing out of my terminals here will be I. So it's the exact same situation that we had before. So my question to you guys is, what's the equivalent voltage seen by the resistor? We can figure it out just using Ohm's law, just like we figured out how to combine resistors in parallel, right? So if we applied Kirchhoff's voltage law around this loop, we would have negative V1 minus V2 plus V, the voltage drop over our resistor, is equal to 0, which means V, the voltage seen by our resistor, is simply V1 plus V2. What would happen if I change the polarity on that voltage source V2? What if I connected it positive polarity terminal on the left, negative polarity terminal on the right? V1 minus V2, okay? So when the voltage sources have the same polarity, meaning we see the negative terminal first in both cases, they add together. When they are of opposite polarities, we wind up performing a subtraction operation. Chester.
How did you know that the resistor is negative?
The voltage drop across my resistor is positive because I see the positive polarity terminal first.
Are you starting in the top right corner?
starting in the bottom left corner and working, following that current around. That is my modality for applying Kirchhoff's voltage law practically every time. Start at the bottom left-hand corner, follow my current around the circuit. Can you guys think of an instance where you have combined voltage sources in series in your practical lives?
Battery packs, multiple battery packs.
Exactly right. You have been combining voltage sources in series anytime you have ever changed the batteries in a remote control or anything like that. You've probably been doing this the better part of your entire life. You just didn't really realize what you were doing, okay? So, as I said, voltage sources in series, when the voltage sources have the same polarity, meaning when we follow the current around its path, we see the same terminal first. So either negative first for voltage source 1 and then negative first for voltage source 2, or positive first for voltage source 1 and then positive first for voltage source 2. We add them together. When they are of opposite polarities, we subtract. Okay, nothing wild or difficult there. That is actually the reason why if you put your batteries in backwards in a remote control, it doesn't work. Because you're subtracting, like if you have a remote control that requires 2 AA batteries, and you connect them in series, negative, positive to positive, and then negative, it sees 0 voltage. The remote control won't work. All right, now let's talk about voltage sources in parallel. And I'm going to do this one as a numerical example because it's very important. So I have 2 voltage sources connected in parallel to some load resistance R, where the voltage drop over my resistance R is going to be this V, or equivalent voltage. And here is my current I. And let's say that this guy is a 5-volt source and this guy is a 5-volt source. What is the voltage seen by my resistor? 5 volts. Does it matter at all that there are 2 of them? No, not even a little bit. So whenever we have voltage sources that are in parallel and they have the exact same voltage, we could replace them with a single voltage source and the circuit would be absolutely identical. Okay. What happens? This is what we do when we're wiring up solar panels and stuff like that. So if you connect, you often connect solar panels to be in parallel, and what that does is it lets each solar panel contribute more current to the load while maintaining that fixed voltage. That's also largely what I do at my job over in Bossier when I'm doing large-scale battery resources, voltage sources in parallel. So what if I have this situation? What voltage is my resistance? So after 3, the average for, the correct answer is how the hell should we know? We've broken the laws of our circuit analysis, right? Yeah, they're in parallel with different voltages. That doesn't work. So if you see anything like this, you can't actually solve it using circuit analysis techniques. Now we could physically make a system like this all day long, right? We could take one voltage, one fresh battery, and one relatively discharged battery, and wire them up in parallel. And what we would see is that one battery effectively works to charge the other one, if that's possible. If you couldn't connect voltage sources in parallel that had different voltages, you couldn't charge a battery. Literally, you couldn't charge a battery. But from a circuit analysis perspective, we have to throw this away. We can't really do anything at all with it. If we want to do anything with it, we have to take into account the resistance of the wires and all that kind of stuff that would limit current flow. And we don't do that because we consider wires to be perfect conductors. Okay? I don't think this will actually show up in anything that I'm going to ask you to do for this entire class, but it is a reasonable question, so I decided to address it. Now let's look at current sources. And we're going to look at current sources in parallel first. So let's say I have some current source I1, some current source I2 connected to my loading resistor R. As a simple application of Kirchhoff's current law, we should easily be able to determine what our equivalent current seen by the resistor is in this case, right? So what should it be? I1 plus I2, right? So what would happen if I change the direction of one of those currents sources? A subtraction operation, right? So when current sources in the same direction are connected in parallel, they add together. When current sources of opposite directions are connected together in parallel, the current subtract. Okay, so very similar to what we saw with voltages, but slightly different. Current sources in series. I'm just going to go ahead and break it down for you. I'm not even going to bother writing it down. Current sources in series have to have the exact same value of the current to be able to combine them. If they don't, everything breaks down. There is literally no practical application I can think of to where you connect two current sources in series, which is why I'm not even bothering to really go through the motions here. I have multiple years of experience dealing with analog electronic circuits and all this kind of good stuff, and have never once dealt with anything that involved current sources in series. So it is what it is. All right. So the big takeaways from this last 15 minutes or whatever of lecture: voltage sources in voltage sources in series add together, current sources in parallel add together. Or a better way to say that would be, I can combine current sources in parallel and I can combine voltage sources in series. Everything past that is really only important for people that go into like power systems engineering and all that kind of stuff. Okay. All right, our next topic is the concept of voltage division. We're going to talk about voltage division and current division today. And then we have an in-class assignment. Technically, we also have a lab to do today, but I don't know that we're going to have enough time. So if we don't, we'll take care of it on Wednesday. All right. Does anybody remember what the voltage divider circuit from your engineering 120 classes look like? Nobody has a clue. All right, that's perfectly okay. So in your engineering 120 class, your voltage divider circuit probably looked something like this. You had your 5 volts from your Arduino, and then a resistor in series with another resistor. Let's call this guy R1, this guy R2, and then this was your output voltage, which was usually connected to some analog pin. And the resistor R1 or the 2 might have been some sort of detecting resistor, so like an LDR or photoresistor or something like that, or it could have been a negative temperature coefficient thermistor, I think is the right word. Yeah, sorry, spacing out there or whatever. Where you were able to do what's called simple voltage division here to figure out what the output voltage is based on the resistor values alone. You never really needed to know how much current was flowing through the circuit. We're going to develop a similar relationship, or it's actually the exact same relationship, but we're going to look at our style of circuit to where we have some voltage, let's call it VDC, connected to some resistor R1, which is connected in series to some resistance R2, which is connected in series to some resistance Rn. So each of these resistors will have an associated voltage drop. So let's call this guy VR1, this guy VR2, and this guy VRN. This right now looks exactly the same as what we use to figure out how we combine resistors in series, okay, as it should. This is a single loop circuit, meaning that all of our elements carry that common current I. And so if we apply Kirchhoff's voltage law around this loop, we would find that the voltage being supplied by our DC source is equal to that voltage drop VR1 plus VR2 plus VRN. Using Ohm's law, then this would become I times R1 plus R2 plus all the way out Rn like so. So again, derivation to this point is exactly that of what we saw last Friday when we were figuring out how to combine resistors in series. So the change that we are going to do here is instead of figuring out what V over I is, we're going to figure out what I is in terms of all of these other things, okay? So I could say that my current I that flows through all of these elements is whatever that source voltage is, VDC, divided by R1 plus R2 plus Rn, right? Voltage divided by the total resistance gives us the current flowing through that loop. Nothing really weird. You guys did this over and over again in your engineering 120 classes. What's going to be slightly different now is if I want to find that voltage drop VR1, I can now make a simple substitution here and figure it out, right? VR1 by definition should be I times the resistor value R1, right? Well, this is going to look like our source voltage VDC multiplied by R1 divided by R1 plus R2 plus all the way out Rn. And so I can see that the voltage drop over resistor 1 depends only on the voltage drop across all of the resistors in series and a simple ratio of resistances. So I never actually have to calculate that current in order to solve for it. And I can similarly say then that VR2 is going to follow suit, right? So it would be VDC multiplied by R2 over R1 plus R2 all the way out to Rn. And in general, I can say that the voltage drop over the kth resistor is VDC times RK, my resistor of interest, divided by R1 plus R2 all the way out to Rn, or using my summation notation, VDC times R sub K over the sum from I is equal to 1 to N of R sub I. So what I mean by that is the voltage over the resistor I'm interested in is the total voltage multiplied by the resistor value of the resistor I'm interested in, divided by the total series resistance. And I could alternatively write this then as VDC times RK over REQ sub S, right? So I see some confused looks, which is fair. It's probably notation based. Nothing, no issue with that whatsoever. I don't care if you agree with my notation or anything. I only want you to be able to put this into practice, all right? So let's work a couple of examples. Chester. REQ comma S. So the equivalent resistance of the series combination of everything. So let's say that I have the following circuit. Here's my 10-volt source. I have a 5-ohm resistor. I have an 8-ohm resistor. And I have a 7-ohm resistor. And I want this voltage V5. Applying voltage division, I can say that V5 is 10 volts times 5 ohms over 5 ohms plus 8 ohms plus 7 ohms is going to be 0.5 volts. At no point whatsoever did I have to bother myself with calculating the current. Okay, so this is how you apply voltage division. Now, there are a couple of caveats here that I'm going to talk about. First of which we'll see, what if I want to figure out this voltage V7, the voltage drop over my 7-ohm resistance. But notice that I have the opposite polarity, right? So when I derived everything to use voltage division, let me scroll up here a little bit. All of my resistor voltage drops were of the opposite polarity of my source voltage, right? In the example that I'm giving you now, my resistor voltage V7 has the same polarity as my source voltage. How do you guys think that's going to affect my value?
It just means that your V7 should be negative.
That's exactly correct. Whatever value I get using voltage division, I should just change the sign on it because it's negative. Another way to think of it is that as we defined our current I, that current I is now flowing into the negative polarity terminal. So when we calculate that voltage, we put a negative sign, okay? So nothing wild or crazy here, but it is something that you'll see that'll potentially trip you up and cause you headaches. So if you ever are doing voltage division and you want the voltage with the opposite polarity as what you would expect, simply change the sign on the voltage. It's that simple. right? So in this case, V7 would be negative 10 volts times 7 ohms over 5 ohms plus 8 ohms plus 7 ohms. So gosh, let's see, that's going to be 70 over 20 is negative 3.5 volts, right? I did my mental math correctly. Now, as it turns out, our opportunities to apply voltage division with something as simple as this are going to be fairly few and far between, as you can imagine, right? Just having a voltage source connected to a couple of resistors connected in series, that's easy peasy. So let's look at something slightly different. Let's say I have a 12 volt source now. An 8 ohm resistor, 15 ohm resistor, 10 ohm resistor, the 2 ohm resistor. I no longer have a series simple connection between all of those elements, right? So ostensibly, I can no longer apply voltage division, but I can use my current level of circuits knowledge to make this behave as if it were a simple series connection of elements, right? So what I mean by that, let's look for this voltage V8, and then let's look for this voltage I'm going to call it X just for the heck of it, because it's technically the voltage drop over the 15 ohm resistor and the voltage drop over the 10 ohm resistor, because they're connected in parallel. If I wanted to force this to fit the mold to be able to do voltage division, how would I go about doing it? Anybody have any thoughts? Yes. That's exactly right. That's all you need to do. Just combine those two parallel resistors into a single equivalent resistance. And now this thing is a voltage source connected in series with a bunch of resistors, and voltage division is fair play. You will get to a point, I hope, to where you won't actually need to do that combination itself. You can just add that into your equation. So what I mean by that is you could physically take, or not, I don't want to say physically, but you could, take the steps required to actually simplify your circuit. Or you could say V8 is 12 volts times my 8 ohm resistor is going to go here in my numerator, because I always put the resistor I'm interested in the numerator. And then in my denominator, it's just my series combination, right? So that's going to look like 8 ohms in series with the parallel combination of 10 and 5. That's going to look, or excuse me, 10 and 15. So that's going to be 15 ohms times 10 ohms over 15 ohms plus 10 ohms plus 2 ohms. And the numerical answer for that will be whatever it is. I don't think I can do that one in my head, or at least not as quickly as I did the other ones. 8 plus 6, so actually that's 8 over 16, so it's going to be 6 volts. If my mental math is correct. Apparently I can't do it. If we were going to figure out what I've called Vx here, what change would we make to the equation? I'm not even going to bother figuring out the numerical value, but what change has to be made? You put that equivalent resistance bit up in the numerator, and that's it. right? Because that's what we're trying to find the voltage drop over, is that equivalent resistance. All right. So any questions regarding voltage division? There's going to be a lot of things that we can break down and kind of make look like this, and homework problems and stuff where being able to quickly apply a voltage division will be of use. Actually, let's work one more. Now that I'm thinking about it, because this is similar to something you're going to be asked to do on multiple homework problems. Let's say I have a 15-volt source. Resistor, resistor, resistor. Let's call this one 10, 20, 15, and 25. And I want to figure what this current I-25 is. So we could potentially, there's a couple of different ways that we could approach this. This one is fairly simple. We could brute force it by kind of writing several Kirchhoff's voltage law and Kirchhoff's current law equations and just kind of figuring things out. Or we could do multiple applications of voltage division to figure out what the voltage drop over that 25 ohm resistor is, right? So what I'm saying is that if we know what that voltage V25 is, we could figure out what I25 is fairly easily. Right? So that arguably begs the question, well, how the heck do we figure out what that voltage V25 is? Let's start by figuring out what this voltage V20 is. Okay, so V20 is going to be 15 volts times, so we're going to have a gnarly looking numerator here, right? How are we going to, what should my numerator be? $15 plus 25 is part of it, so I'm going to write that down. So that voltage V20 represents the voltage drop over the 20 ohm resistor, which is in parallel with a series combination of 15 ohms and 25 ohms, right?
20 times that over.
Yes, so 20 times this over the sum, right? What's going to be in my denominator? 10 plus that thing, right? Now that that voltage V20 is arguably known, we could just substitute in the numerical values and get some finite concrete answer for that. How could we figure out what that voltage V25 is?
Would this be the 25 ohms, or would be the voltage across 25 ohms over 15 volts?
Exactly. So we can apply voltage division again, where V20 is now a known voltage, which allows us to do voltage division over just the right-hand portion of the circuit. So we have a fairly gnarly looking circuit here, multiple different currents to take care of if we wanted to go that route. But we can actually figure out what that voltage is and then what that current that we're finally interested in is without ever calculating any of those intermediate currents, right? So this can be a very, very powerful tool. It just requires a reasonable amount of practice to employ. So here we'd have 25 ohms. And then here we would have 15 ohms plus 25 ohms. And then substitute in our numbers. Okay. All right. The next thing, well, anybody have any questions about this before we move along to current division? All right, so current division, to my knowledge, was not even remotely covered in your 120 series. All right. So current division is a similar set of steps to voltage division, but it allows us to figure out how much current is flowing through a particular branch that is connected in parallel. Okay. So let's say that we have some current source IS connected to several resistors in parallel. Let's call this guy R1. This guy here will be R2. And this guy out here will be R sub N. So this works for an infinite number of resistors connected in parallel. Because we have a single node pair circuit, we know that all of our elements share a common voltage V. And I am going to define my currents of interest, my resistor currents, to be IR1 direction down, IR2 direction down, and IRN also direction down. So if we apply Kirchhoff's current law, we could see that our source current IS is equal to IR1 plus IR2 plus IRN. And we could use Ohm's law to express all of those currents in terms of that common voltage V. So that would look like V multiplied by 1 over R1 plus 1 over R2 plus 1 over R sub N. If I stopped here and took V over I, this is how we got the equivalent resistance for combining resistors in parallel, right? So instead, I'm going to figure out what my voltage V is. My voltage V should be, let's see here. IS divided by 1 over R1 plus 1 over R2 plus 1 over R sub N, like so. And now I can say that my current IR1 is just V over R, right? Or V over R1. So I'm going to write this down in what's going to look like a fairly interesting way. IS, and then I have 1 over R1 divided by 1 over R1 plus 1 over R2 plus 1 over R sub n. So it winds up being a very similar formulation to that we saw for voltage, except that now we wind up using the reciprocals. And it's because all of the elements are connected in parallel, not in series. Okay? So another very interesting observation here, or at least it's interesting to me. I could write this as IS divided by R1 multiplied by 1 over R1 plus 1 over R2 plus 1 over R sub n. What does everything that I have in the square braces represent? The equivalent resistance of all of those resistors connected in parallel. So this really simplifies down to IS times REQ comma P, the equivalent parallel resistance divided by the resistance of the resistor that I'm interested in. So it's almost identical to our voltage source definition, except that the equivalent resistance is in the numerator when we're doing current division, and it's in the denominator when we're doing voltage division. There is a shorthand for doing current division with only 2 resistors in parallel, but I am intentionally not teaching it to you. The reason why I say this is because if you look in your textbooks and stuff like that, you might see some current division equation that doesn't have all these pesky reciprocals in it, okay? That expression is literally only valid for 2 resistors and 2 resistors alone. And the reason why I don't like teaching it is because it winds up having the resistor you're not interested in the numerator divided by the sum of the resistors. So it's a really weird rule set to think about of, in this way, in the numerator, I have the reciprocal of the resistor I'm interested in divided by the reciprocal of all the resistors in parallel, which is very, very similar to how it looks for voltage division, where it's the resistor I want divided by the sum of the series resistance. If I show you that other method, then you have to start thinking about, well, what's the resistor I'm not interested in, and where does that fit into the equation? And it gets all wackadoo real quick, okay? So I'm just warning you, you may be studying this type of stuff with some of your cohorts that are in different sections. And there's a very distinct possibility that they didn't cover this way of determining current division. This works for any number of resistors connected in parallel. The way that they potentially learned only works for 2. This is a much more powerful tool to have. Okay, so I just want to be clear about that. All right. So let's put this into practice. Let's say that I have a 5 amp source and then I have an 8 ohm resistor and a 4 ohm resistor. And a 2 ohm resistor. And I want to find this current, let's call it I8, direction down. and I want to find this current I2 direction up. Right? So notice that current I2 is in the opposite direction of what we have defined to be normal for current division. So what we're going to wind up doing there is, again, just changing the sign on it to make it agree. Okay. So I8 is going to be 5 amps times 1/8 ohms divided by 1/8 ohms plus 1/4 ohms plus 1/2 ohms. So let's see, 1 plus 2 plus 4 is 7. So 5/7 of an amp. If I'm not mistaken. By all means, verify my mental math here, because there's a distinct possibility I did something dumb. 1 plus 2 plus 4 is 7, right? So 1/7 times 5, 5/7 of an amp. Sorry, let me scroll back up if it will let me. I2 actually, you guys tell me what my expression should look like to determine I2. Negative 5 amps exactly right. 1/2 in the numerator, 1/8 plus 1/4 plus 1/2, which is going to be 4/7 times 5, so negative 20/7. The current through any parallel path for a known amount of current entering a resistor network. Okay. So let's work another example. I'm going to mess things up a little bit here in a couple of ways. Actually, I shouldn't use 20 there because I've already used 20. All right. So this guy is appreciably different from our last example in 2 ways. One of our parallel branches here has been split up into 2 resistors in series. I feel like you guys can catch on pretty quickly as to what we're supposed to do there. But what about that 20 ohm resistor to the top? How does that mess things up, if at all? Okay, that's the key. It has a, so you're correct that it is going to introduce a voltage drop into the system. That being said, current division is allowing us to calculate currents without ever knowing what any voltage in the system is at all. So that doesn't particularly matter, right? We know that all 6 amps of current flows through that 20 ohm resistor before it sees that middle branch containing the 10 ohm resistor and that right-hand branch containing the 30 ohm resistor and the 5 ohm resistor. So if we are using current division to solve for that current I-10 or that current 5, the 20 ohm resistor should never show up in any of our equations because all of it flows through that one, okay? So with that in mind, what should our equation for I-10 be? 6 amps, which is the amount of current that's flowing into our parallel resistor network, okay? What comes next? 1/10 ohms, all right. What comes next? 1/10. Yeah, 1/30 plus 5. Or 1/35, however you want to do it. So we effectively treat those two resistors in series as a single equivalent resistance that is in parallel with our resistor of interest. What changes for I-5? All right, so we're going to have 6 amps. Our denominator is going to stay the same. What should our numerator be now? 1/35, not just 1/5. Okay, we have to take the entire resistance of that branch into account. Put it in a calculator. I don't think I can do that in my head, and I'm not going to bother trying. All right, so that has been source combination. Just to recap, voltage sources in series can be combined. If they have the same polarity, they add together. If they have opposite polarities, there's subtraction involved. Current sources in parallel can be combined. If they have the same direction, they add together. If they're of opposite directions, subtraction is involved. Then we talked about voltage division, which allows us to calculate the voltage drop over any series or any resistor in a series connection without ever having to calculate any current, as long as the voltage drop over the combination is known. And then we talked about current division, which allows us to calculate the current flowing through any branch of a parallel combination without ever having to calculate any voltages, as long as the current entering the network is known. Any questions on any of that stuff? I know it all seems straightforward and easy right now. I hope you continue to think that way, but I sincerely doubt that you will. So that's the purpose of in-class assignments, legitimately. It's for you guys to leave my lecture portion of it thinking, this isn't that hard, and then have it in front of you and go, oh crap, maybe it is. And then you can ask me a question. So we actually have a reasonable amount of time to go over it.